In the last class, we saw that Heisenberg's uncertainty principle restricts the simultaneous measurement of position and momentum of an object with arbitrary precision. We have also seen uncertainty relations connecting energy and time, and also in the case of angular momentum and its orientation. Today we are going to discuss some of the consequences of uncertainty principle. So let's try to calculate the minimum energy of an electron in the hydrogen atom, in the ground state of the hydrogen atom, using uncertainty relation. For this, we use the uncertainty relation between the position and momentum, which can be approximated as delta x delta p is greater than or equal to h cross. As you know, in a hydrogen atom we have a single electron which orbits around the nucleus. So we are trying to calculate the energy of this electron, or in general the energy of the atom in its ground state. Now the maximum uncertainty in position measurement delta x will be of the order of the Bohr radius of the hydrogen atom. A is used to represent the Bohr radius of the hydrogen atom. Now we assume that the maximum uncertainty in momentum will be of the order of its momentum itself. Hence, we can write from the first equation that the momentum will be of the order of h cross by A. Now, we know that the total energy must be the sum of the kinetic energy and the potential energy, and hence we have a relation E equal to P square by 2m minus 1 by 4 pi epsilon 0 E square by A, where this first quantity represents the kinetic energy and the second quantity represents the potential energy of the electron. If we substitute h cross by A for momentum, we get the relation E must be greater than or equal to h cross square by 2m A square minus 1 by 4 pi epsilon 0 E square by A. For the ground state, this energy will be minimum, and hence if we differentiate the expression for energy with respect to the radius A, it must be 0. That is, dE by dA must be 0, and when we differentiate it, you get this expression. So equating it to 0, we can get an expression for the minimum radius, which we denote as A0, and from this expression it gives you that A0 equal to 4 pi epsilon 0 h cross square by m E square. If we substitute this value of A0 in this equation, we get E0 greater than or equal to minus m e raised to 4 by 8 epsilon 0 square h square after simplification. Since we have this inequality here, it says you that the energy of the ground state, the suffix 0 represents it's the ground state, the energy of the ground state must be greater than this quantity, or you can say that the minimum of this energy will be when we use this equality here. Okay, so the minimum energy of the electron in the ground state of the hydrogen atom is given by E0 equal to minus m e raised to 4 by 8 epsilon 0 square h square. You can see that this is what exactly the ground state energy of the electron in the hydrogen atom. So starting from the uncertainty principle, we get the same expression for the energy of the electron in its ground state, like what we get if we do it with the other methods. The next case we are going to analyze is the non-existence of electron in the nucleus. For a long time it was believed that electron is a part of nucleus. So we can use uncertainty relation to prove that electrons are not nuclear particles. A typical atomic nucleus has a radius of 5 into 10 to the power minus 15 meter. If you take the uncertainty in position as this order, we get the uncertainty in momentum as delta P greater than or equal to h cross by 2 delta x from the uncertainty principle. So substituting the various values, we get delta P greater than or equal to 1.1 into 10 to the power minus 20 kilogram meter per second. So this number you get after you substitute the value for h bar, which is h by 2 pi, and substituting the value of delta x, which we assume as of this order, nuclear radius order. So its momentum will be greater than 1.1 into 10 raised to minus 20. So that means the momentum itself must be at least of this order, right? It can be greater than this value, but the minimum value of momentum will be at least of the order of uncertainty in momentum itself. Then the kinetic energy of this electron is given by the relation Pc, kinetic energy equal to Pc, and if you substitute for the value of momentum and also the value of speed of light, you can see that this kinetic energy must be greater than or equal to 3.3 into 10 to the power minus 12 joule. In terms of electron volt, this corresponds to a kinetic energy greater than 20 million electron volts. However, experiments show that the maximum kinetic energy of electrons emitted by nuclear reactions is less than 2 million electron volt. Since there is huge difference between the actually observed kinetic energy of the electrons and what we expect if we consider electron as a nuclear particle, we can assume that the electrons cannot exist inside the nucleus. If it was a nuclear particle, the kinetic energy, experimentally observed kinetic energy, would have been greater than 20 million electron volt. Since we are not observing that, it's a clear indication that electrons cannot exist inside nucleus. Now the third case we are going to analyze is the width of the spectral lines. As you know, all kinds of spectral lines show a finite width due to many reasons. One of the reasons is the natural broadening of spectral lines, which is a direct consequence of uncertainty relation. You know that spectral emission happens when an electron makes a transition from an excited energy state to the ground state or a lower energy state. Then the frequency of the emitted photon must be exactly equal to the difference in energy of these levels divided by the Planck's constant. So we expect a sharp line spectrum like this one. But in reality, we get a spectrum with a finite width. So let's see what is the role of uncertainty principle here. Atoms remain in an excited state for a finite time called the lifetime tau. Hence, the uncertainty in the time will be of the order of tau. Then from the uncertainty relation, delta E delta T greater than or equal to h cross by 2, we have the uncertainty in the excited state energy as delta E greater than or equal to h cross by 2 tau. Then energy, as you know, it is given by the expression h nu. So the uncertainty in energy can be expressed in terms of uncertainty in the frequency. So h delta nu must be greater than or equal to h bar by 2 tau. For most of the states, the tau is of the order of 10 to the power minus 8 second. So the uncertainty in the frequency of the emitted spectral line is it must be greater than or equal to 1 by 4 pi tau, which corresponds to a spectral width of the order of gigahertz. If you substitute for this tau here, this will be a number greater than 10 raised to 9 hertz. So you can expect that uncertainty principle will never allow us to get a sharp line spectrum, because you will always have a natural broadening delta nu in the frequency spectrum or in the spectral emission of the atoms or molecules, which is of the order of gigahertz. So we can never expect sharp spectral transitions.